Good morning, everybody. Let's go ahead and get started. Thank you for joining in today. So first things first, I want to see your hand raised if you can hear me all right. Okay, perfect, perfect. Thank you for letting me know. You can go ahead and lower your hand. Okay, now let's begin from where we left off and we'll try to make some progress. Today we'll be meeting for lab at noon as well. Okay, so this is what we did in the last class. We did this problem of a three-stage amplifier, three stages. And each stage has its own input resistance and output resistance. Okay, we did this problem to see how there is signal loss between our input resistance and our output resistance. Okay, and I also showed you how we have to be careful when we are connecting the output load 100 ohms. We cannot directly connect that to a really large output resistance. Okay, there's a big significant signal loss. All the different considerations we have to take into account when we have to match the load and input resistances, load and output resistances as well. Then we talked about the four different types of amplifiers. For all the four different amplifiers, I mentioned the governing equation is this guy. Output is gain times input. Okay, depending on what the input variable is and what the output variable is, we have four different kinds of amplifiers. If both the input and the output are voltage, like in figure 1, then we have a voltage amplifier. Okay, so if the input is current and the output is also current, like in figure 2, then we have a current amplifier. And we define a corresponding current gain. Now take a look at number 3 here. If the input is a voltage and the output is a current, then we have a transconductance amplifier. An example for that is a MOSFET. Okay, the input is a voltage, output is a current. Similarly, if the input is a current and the output is a voltage, then we have a trans impedance, a trans resistance amplifier. Corresponding to that, we can define a gain of Rm, which is output over input. So the gain is always output over input. Okay, so this is what we discussed in the last class. In addition to that, okay, so we looked at some problems. In addition to that, I kind of described to you an approach to find output resistance. So this is R output, not root. This is R output. How do you find the output resistance? And I mentioned there is a general approach to find the output resistance is to apply a test voltage and look at the test current. Okay, test voltage, that is Vx, and calculate the test current Ix. Now, if you massage your equations to represent Vx over Ix, we can get an analytical solution for R0. Okay, we are going to see application of that in today's class. Okay, in order to do that, you have to first begin by making your source voltage or source current to 0. Okay? So if you have a source voltage, if your input is a voltage, then you tie that input source to ground. On the other hand, if your input is a current, you open circuit. You make the input 0 by um, making the current source open circuit. Okay, so the general step, the general approach to finding the output resistance is to kill all independent sources. Okay, all independent sources, you make them zero. Okay, independent source, if it's a independent voltage source, you short circuit it. If it's a current source, you open circuit it. Then you apply a test voltage, okay, and look at the test current. You could do the opposite. You could apply a test current and look at the test voltage. But you are interested in finding output resistance, which can be expressed as Vx over Ix, V test over I test. And that's your goal, okay? So that's the goal eventually. So we'll see an application of that in today's class, okay? In order to find the R output resistance, R out. Okay, that can be found out by this test voltage, test current method. Okay, then we talked about the amplifier frequency response. Okay, the two things that we want to remember is there is a gain between what we apply and what we see on the output. Okay, so the input amplitude and the output amplitude are different. So VO over VI will give you gain. Okay, gain is usually expressed in dB. Okay, that's gain over here. So in addition to that, in addition to the difference in the amplitude itself, you want to pay attention to the fact that the output has a phase. Okay, the output has a phase that is not present in the input. Okay, so the phase response is shown in here. Okay, so the output is different from the input in terms of the amplitude and in terms of the phase. Okay, and in order to understand how this phase depends as a function of frequency and how this amplitude depends as a function of frequency, we understand this from AC analysis. So this information about how the voltage and phase of an amplifier output depend on frequency, we do what is known as AC analysis. This is something we discussed in the last class. Okay, so here is an amplitude frequency response of an amplifier. Okay, so bunch of things that we want to remember is that there's a roll off in amplitude. Okay, first of all, along the x-axis is the frequency, along the y-axis is the amplitude of gain, is the magnitude of gain, V output over V input, expressed in log base 10, 20. Okay, so that's the magnitude of gain along the x-axis and along the y-axis, and along the x-axis I have the frequency. Okay, two observations is at really low frequencies. The two observations that we want to make are that at really low frequencies, remember, the gain is rolling off. And in addition to that, see, at high frequencies, the gain is rolling off. Okay, this is an example of AC coupling. AC coupling. So the low frequency roll off is brought about by the external capacitances. External capacitances are large. Okay, external capacitances are large, and the parasitic capacitances are small. The roll off on the right, shown in purple, is brought about by small parasitic capacitances. Okay, small parasitic capacitances that are part of the transistor used for building the amplifier circuit. Okay, the one on the left is brought about by external capacitances, and by external capacitances I mean something like this. Okay, the coupling capacitance that's used for coupling AC and blocking DC. Okay, so we looked at all of that in the last class. But what is important to remember is good amplifiers have a very wide range through which the gain is more or less very constant. Okay, this difference between omega 1 and omega 2 is defined as bandwidth. Okay, so this is AC coupled response. AC coupled external coupling is present here.
Professor,
Okay,
if we
yes.
define if we have to define bandwidth, how will we define it?
Usually the bandwidth is defined for low pass and high pass filters. The idea is you have the pole frequencies. Look at this. This one, omega 1, is called as the pole frequency. There's one pole over there, and there's another pole over here, omega 2. The difference between these two is called as the, so there is one RC at a really low frequency coming because of one omega 1 RC is coming because of the R and C at really low frequencies, and there is an omega 2 at high frequencies that is coming because of parasitic capacitances. The difference between these two is defined as the bandwidth. Okay, so numerically speaking, the difference between omega 2 and omega 1 is the bandwidth. A more intuitive way to understand is the range of frequencies of an amplifier over which the gain is relatively constant. That's the idea of bandwidth. Okay, at omega 1 and omega 2, the overall gain is 3 dB less than the peak gain. Does that make sense?
Yes.
Okay. So here is an example of capacitive coupling where the DC voltage or the DC bias of the first stage is decoupled from the DC value of the second stage. Only the AC components are coupled. There's only AC coupling, AC signal is coupled. This is something we looked at in the last class. So there are three kinds of amplifiers that we show here. An AC coupled amplifier shown in this figure, an AC coupling. Okay, a DC coupling amplifier. So that's let's see, that's AC coupled amplifier. Then there is the DC coupled amplifier. You see, there is no roll off at the low frequencies. The low frequency is coming because of external coupling capacitances. Okay, so that's the DC coupled. Then there is the band pass filter. Okay, the band pass filter, which has which amplifies only around frequencies around a center frequency. Okay, that's the idea of amplifier frequency response. Then we went into in the last, yes.
Like in DC coupling, so so we remove the AC component of the signal.
No, we couple both the AC and the DC component. We remove the capacitor. Okay, we remove this capacitance is not there. Okay, there is a direct coupling.
Okay.
So the AC component is also connected to the second stage. Similarly, the DC component as well. Okay, as opposed, so both AC and DC are coupled here. If there is only DC coupling like shown here, there's only AC coupling like I'm showing here using a capacitance, then the DC values are separate for each of these stages. Does that make sense?
Yes.
Okay, so we looked at single time constant, and I mentioned that this value, the product of RC, has units of time. Okay, units of time. So 1 over RC will give you an omega. 1 over 2 pi RC will give you frequency. Okay, and based on that, I have high pass or low pass circuits. Okay, the one shown on the right is a high pass circuit because a very easy way to understand is what happens at really high frequencies, at extremes, at really high frequencies, the capacitance acts as a short. Okay, the capacitance acts as a short, and then all the voltage that is applied here shows up. All the voltage that is applied here drops at the through the resistance. So the capacitance disappears, and all the voltage is passed through the resistance. Okay, that's the idea. And at really low frequencies, let's see what happens at really low frequencies. At really low frequencies, the capacitance acts as an open circuit. Okay, the capacitance acts as an open circuit. There's no voltage drop across resistance R0. So the capacitance blocks low frequencies and passes high frequencies. Therefore, it's called a high pass circuit. Okay, and in between the very low frequency DC and the very frequency, the interaction between R and C, that is what determines the transfer function of this high pass circuit. Similarly, for the low pass circuit, at really really high frequencies, this is going to act as a short, and there is no voltage drop across that resistance. Okay, across that capacitance. At really low frequencies, I'm talking about DC. At really low frequencies, this capacitance acts as an open circuit. Okay, and all the voltage that is applied here, VI, shows up at output V0. Okay, um, there is no capacitance acts as an open circuit. Okay, so it's a low pass action. Okay, so it's all based on the idea that capacitance acts as cap, acts as open circuit to DC, and cap acts as a short circuit, high frequencies. Okay, so that's the idea. And then if ZC is the impedance of a capacitance, okay, then ZC plus ZR, ZC plus R is the total impedance of the resistance and capacitance in series. Then we have the transfer function. Okay, so the transfer function is always defined as V out over Vn. The transfer function can be expressed using these complex impedance ZC plus R. Okay, it's something I discussed in the last class. Then we went on to talk about Bode plots, just barely enough. Okay, I talked about Bode plots. So let's say the idea of Bode plot, let me begin there, is that at pole frequency, at a particular pole, at pole frequency, at that frequency, a very crude approximation, okay, a very crude approximation is that the magnitude of gain begins to fall. Okay, and for single pole, the slope is always minus 20 dB per decade. Okay, so the gain is going to roll off at 20 dB per decade. Okay, and then about the phase, what happens is the pole begins to affect the phase at 10 times below the pole frequency. That's this guy, and it has its effect up to 10 times above the pole frequency. Okay, so at 10 times below the pole frequency, the phase begins to fall at negative 45 degrees per decade, negative 45 degrees per decade. So the idea is one pole, single pole, contributes to 90 degrees degradation in phase. Okay, overall, beginning from from 1/10 of the pole frequency to 10 times the pole frequency. Okay, that's the idea. This is what we would expect to see with phase response. This is the idea of Bode plot. Okay, so the Bode plot can also tell us what happens if there is another pole over there. Okay, the assumption is that pole 2 is much farther away from pole 1, at least greater than 10 times the pole 1 frequency. Okay, then we can see the effect of pole 2 as well. In the presence of pole 2, what happens to the magnitude? Then the magnitude begins to fall at 40 dB per decade. Okay, let me see if I can quickly show here. Okay, that's a little beyond the scope of this class. We are not interested in two-pole response. So the assumption is that the pole 1, 10 times the pole 1 is less than 10 times the pole 2. Okay, or 1/10 of pole 2 over 10, pole 2, and pole 2 times 10. So the idea is that the gain begins to fall at that frequency at P1. Okay, and it continues to fall at 20 dB per decade until it hits pole 2. At pole 2, the effect of pole 2 is also adding on, so it begins to fall at minus 40 dB per decade. Okay, so that's the idea. What happens when this pole 2 is moving closer than P1? That's all interesting discussions that that are beyond the scope of this class. 109, 230 class, all of those talk about the relative sizing of the poles and more than the behavior of a circuit with more than one poles. Okay, so that's beyond the scope of this class. We are only interested in single time constant circuits for now. What happens when there is one good pole? Okay, the magnitude begins to fall at that pole frequency, and the rate of the slope is going to be negative 20 dB per decade. And when it comes to phase, shown below, the phase begins to fall at 1/10 of the pole frequency, and it continues to fall at, until 10 times the pole frequency. And after that, the pole does not affect the phase anymore. Okay, so that's the idea. So here is the low pass single time constant response. So the approximation I made was along these lines. Okay, the approximation I made was along these lines. Okay, let me see, style that. So shown in blue is the approximation, and the real behavior is going to be along those lines. Okay, so there is a slight difference between the real behavior and the approximation. Even so, the approximation I made here was that the gain begins to fall at the pole frequency. But in fact, as a matter of fact, the gain begins, the magnitude of the gain begins to fall a little before the pole frequency. And at exactly the pole frequency, the gain will have reduced by 3 dB. So if this guy was 20 dB to begin with, okay, at the pole frequency, the gain is going to be 17 dB. Okay, similarly, if the gain is 0 dB, then at the pole frequency, it's going to be negative 3 dB. Okay, so that's the idea. That's the behavior of magnitude with respect to frequency, the magnitude of gain with respect to frequency. As the frequency increases, for a single pole behavior, for a pole at that frequency, it begins to fall at 20 dB per decade. Okay, questions, please.
I have a question.
Yes.
Okay, so if we want to determine the magnitude of the voltage gain, and we're given a frequency, how we know which, if we're using the 20 log or the 3 log on this scenario?
There are two ways to find out. Okay. So the question is, let me repeat your question to understand if I, to see if I understand correctly or not. If I give a particular frequency, F1, okay, and you want to find out the gain at that frequency, okay, so what we do is, remember the transfer function I mentioned, gain is given as V out over V in at that particular frequency. Okay, you can express this in terms of j omega. Okay, so when you express this in terms of j omega, the transfer V out over V in will give you the gain, and V out over V in, as you can see, has a frequency component. Okay, if you see this guy V in, this guy V out, what is V out over V in? V out over V in is ZC over ZC plus R. But ZC, you know to be 1 over J omega C, right? 1 over SC. So what you can do is, at a given particular frequency, F, which translates to omega, you can calculate ZC, and you can calculate this total expression ZC. Does that answer your question?
Well, that's part of the process, and I think that I already figured it out. What I cannot really fully understand is what when you have to go from that to get the decibels.
Okay, so once you have V out over V in, okay, let's say that comes out to be 1000. Okay, all you have to do is 20 times log of that guy. So that is going to come out to be 20 times log 1000 base 10 is 3. So it's 60 dB. 20 log 1000 base 10.
I see. So is there any way that we use that 3 log in any of these problems, or is always going to be 20 log, whatever our result from B out and B in?
It's always 20 log. It's always 20 logs. And this is the result. That 1000 there is the result. Okay?
Great. Great.
It's always 20 log result base 10.
Sounds good.
Does that make sense? Yep.
Yeah,
perfect. Good. I'm happy if you're asking questions. Okay, so good. So that's the idea of low pass filter. That's the idea of low pass single time constant response. Okay, the magnitude response of a STC single time constant low pass rolls off at minus 20 dB per decade, which is also similar to 6 dB per octave. Okay, this is called a single pole roll-off. Remember, I showed you minus 40 per decade when there are 2 poles. But we don't care about that in this class. We are only interested in single time constant, which amounts to 20 dB per decade. Okay, when it comes to the phase begins to affect at 10 times below the pole frequency. So that's my pole frequency right here. Okay, 1 is the pole frequency shown over there. Okay, now 10 times below that pole frequency is when the phase begins to fall, and it continues to fall until 10 times the pole frequency. Okay, and then it stops rolling off. That's the phase. The phase only is effective from 10 times below to 10 times above. So at exactly the pole frequency, the phase is 45 degrees below 45 degrees below the input. Okay, so that's the idea. So single time constant 1 over RC expressed in omega is called as the 3 dB frequency. because like I mentioned earlier, at exactly the pole frequency, at that value, the magnitude is 3 dB less than what you initially began with. Okay, so if this was 50 dB, then this is going to be 47, always at the pole frequency. Okay, so that's the idea of pole frequency. Okay, and you see these numbers 0 for magnitude here because you are normalizing. So all of these are normalized values. The magnitude of the gain is normalized, okay, and also the pole frequency is normalized. The frequency is also x-axis is also normalized to the pole frequency, okay, at 1 times omega naught. That's the idea. It's all normalized. So the same can be thought of in terms of the high pass response, except that it happens in the low frequencies, and there's a roll off at minus 20 dB per decade, or there is an increasing slope. As you increase the frequencies, the slope is going to be constant. The magnitude is going to increase at 20 dB per decade. Okay, so the magnitude is going to raise at 20 dB per decade, and this is for high pass single time constant circuit. What you want to remember is for both low pass and high pass, the phase still is going to fall. Okay, what is going to be different is how the magnitude changes. For high pass circuit and the low pass circuit, the phase is going to fall only. Okay, as on the other hand, for a low pass circuit, the magnitude of gain rolls off. Okay, the magnitude of gain rolls off, as opposed to a high pass circuit where the magnitude of gain increases. Okay, that's the idea for high pass circuit, and it flattens at 3 dB frequency. Okay, and this number 1 over RC is an important number. That gives us the time constant, that gives us the pole frequency, that gives us the frequency. Okay, the 3 dB, omega 3 dB frequency. So here is an example that we can understand and we can solve in terms of the frequency response. Okay, let's see. Amplifiers typically have parasitic capacitances at both the input and output, which short out the signal and thus reduce the gain as frequency increases. So let's do a little mental thought experiment. Let's see, there is a parasitic capacitance, CI. Okay, let's say there is a capacitance. What do you think happens at really, really high frequencies?
Like at very high frequencies, capacitor allows it to pass.
Correct. So remember, there are two parallel paths here, right? There are two parallel paths, one through the resistance and one through the capacitance. So all of a sudden, capacitance provides a short, a zero impedance path. So most of your signal is going to go through this capacitance, through ground, and then there is going to be very little to zero voltage across this resistance. Okay, there's going to be no voltage across this resistance, and when there is no voltage across this resistance, there is nothing to amplify. Okay, so the very idea of amplification is negated because of the short circuit of a capacitance. The capacitance at high frequencies provides a short circuit that bypasses the resistance. Therefore, the amplification is killed. Okay, that reduces the gain at high frequencies. Okay, that is because of the parasitic capacitances. Okay, because of parasitic capacitances, the gain is drastically reduced at high frequencies. Okay, so let's first do the problem in the textbook without taking into account the parasitic capacitances. So we're not going to look at this capacitance first. Okay, so let's try to find the gain at DC. Okay, you're interested in finding the gain at DC. This is pretty similar to what we did in the last class. Okay, what we did in the last class is to see VI in terms of VS. VI is really RI because of the voltage division, RI over RI plus RS. Okay, then that's the voltage division here. Then remember that gets multiplied by mu. So that's this mu over here. Then there is a voltage division between RL and R naught. So V out is really RL by RL plus R naught times the voltage that I see here. So that's exactly what we did, similar to what we did in the last class. So if you factor out Vs through that and divide it by V naught, you're left with this expression. The gain at DC is the intrinsic gain mu times the voltage division at the input side times the voltage division at the output side, signal loss because of that. Okay, that's the gain, and you end up with what is a 40 dB gain. Okay, 40 dB gain is always 100. Okay, a 40 dB gain, 1000 gain is 60 dB. So you can see the relationship. Okay, a gain of 10 is 20 dB. Okay, a gain of 10 is 20 dB, and a gain of 1 is 0 dB. Okay, gain of 1 is 0 dB, 10 is 20 dB, a gain of 100 is 40 dB, so on and so forth. Okay, you can see the idea. Now we want to find out the F3 dB. F3 dB, if you remember, is always 1 over RC. Okay, F3 dB is 1 over RC. How do you find, well, you know C here, over here, right? You know C. How do you find R? Looking into the circuit, okay? That is where we have to apply the technique that I described earlier, okay? So here is the technique that you described. Let's see. I have a resistance, RS, and another resistance, RI, in parallel with the capacitance, CI. Okay, and then there is a voltage source, Vs. Okay, now you are interested in finding the R and C at this node so that you can calculate 1 over R times C to give you omega 3 dB. Okay, that is what we are trying to find in this problem. If you divide that by 1 by 2 pi, if you divided that by 2 pi, then you have F. Okay, so your goal is to find the equivalent resistance here. Okay, and the capacitance. The capacitance is straightforward. You can see that capacitance CI over there. Okay, CI. How do you find the resistance? Okay, in order to find the resistance, earlier I mentioned that you have to make the independent current sources 0. So what you have to do is to tie this guy, short circuit your voltage source. So you get rid of this voltage source and replace it with a short. Okay, then what you have here is C in parallel with a resistance R I parallel with RS. So that's the equivalent resistance, R equivalent times CI. So at this node, the value of resistance is Ri parallel with Rs. The capacitance is Ci. Therefore, the pole frequency is 1 over 2 pi r times CR equivalent. And that's exactly what we see here. This is RS in parallel with RI, which is the R equivalent. And then there is the CI, which is the CI. Okay, so you plug that into your calculator, you get this number, 159.2 kilohertz. Does that make sense? Okay. So from that, we can find the unity gain frequency. Okay. So if 159 the idea is that the gain bandwidth product, gain times bandwidth product, is going to be constant. Okay, if your gain is 40 dB or 100 at a particular frequency at omega negative 3 dB, that is exactly going to be the gain times the omega t. So omega t you can find out by 100 times the omega 3 dB. That's exactly what is shown here. Okay, the idea is in order to find the unity gain bandwidth product, you have to understand that the gain bandwidth product is constant for a given amplifier. So that's you don't have to worry too much about it. The idea is how do you find the F negative 3 dB for a given R and C values for a given circuit. Okay, all you have to do is find the equivalent resistance at a node and find the total capacitance at that node. The product of impedance and capacitance, resistance and capacitance at a node gives you the time constant 3 dB frequency at that node. Okay. All right, so let's do another problem here. Problem number 1.24. Okay, so the source resistance is given to be 1 kilo ohms. It's coupled with the capacitance, and then Ri is given to be 9 kilo ohm. So Rs is given to be 1 kilo ohm. Ri is given to be 9 kilo ohm. The question is, find the what is the how big must C be in order to set the low frequency, negative 3 dB frequency, no larger than 100 hertz. So here is the idea: 1 over RC 2 pi should be no larger than, less than or equals to 100 hertz. That's the problem given. Okay, the problem that is given is, the information that is given is, you have to pick a C such that, so let's massage this equation a little bit more. 2 pi RC should be greater than or equals to 1 over 100 hertz. Okay, 1 over 100. Or C should be greater than or equals to 1 over 100 times 2 pi times R. Okay, that's the idea that we have here. So that's exactly what is being found here. Okay, F3dB is calculated to be 1 over 2 pi times C times R equivalent. So the information that is given, the constraint that is expressed in the problem is that this pole frequency should be no greater than, or it should be less than or equals to 100 hertz. So massaging the equation, you'll get a minimum value for C. That's what I want you to see. Okay, so when you solve this problem, the solution that we get here expresses the C minimum. Okay, that's exactly what we are asked to find out. How big must C be? Okay, C minimum. Okay. Questions, please. Questions so far. One K, 9K. So here is the problem. There is a source resistance 1K, which is RS. Then there is a capacitance C. Then there is a RI, 9 kilo ohms. Okay, so the problem is given to be 1 over 2 pi RC, where R is the R equivalent, should be should be a maximum of 100 hertz. Okay, we want to find the value of C. Okay, how do you find R? So it seems that we know just about everything here. If we can find out R equivalent, if we can find out R equivalent, then we have the value of 2 pi, we have R equivalent, so we should be able to find the value of C. Now, in order to find out the R equivalent, we follow the same approach as earlier. Okay, we short circuit the independent voltage source. Then what we have is we have a capacitance that is in series with two resistances. So there is this R equivalent resistance, which is 1 kilo ohm in series with 9 kilo ohms, so which gives me 10 kilo ohms in series with the capacitance here. Okay, so at that particular node, the resistance, the total resistance that this capacitance is 10 kilo ohms. And that's the reason why you see this equivalent resistance to be shown as R1 plus RS. Does that make sense? So something in the chat window. Let's see. It'll be a short circuit. Yes. Okay. Questions, please. So I'm interested in finding 1 over 2 pi RC, and I want that to be less than or equals to 100 hertz. And I know the value of R, which is the sum of 1K and 9K. And I know the 2 pi constant. I should be able to figure out the value of C, which comes out to be C 0.16 microfarad. So if you use C equals to 0.16 microfarad or higher, C equals to 1.6 microfarad, that's good as well. Anything 0.16 microfarad or higher will work. Okay? Questions, please. Okay. So let's continue from there. So that should pretty much cover all the topics for chapter 1. Okay, the key topics that we want to remember are that there are many types of different signals. Signals can be anything that carry information. Okay, analog signals are continuous, both in time and value. Digital signals are discrete. Okay, then there are data converters which are used to convert from analog to digital and digital to analog domain. And then of course there are voltage and current signals. We use different models. Voltage signals are modeled using Thevenin equivalents. Current signals are modeled using Norton equivalents. Okay. Let's see, signals can contain many different frequencies. There are 4 different types of electrical amplifiers. There is voltage, current, trans resistance, and trans impedance amplifiers. Okay, trans impedance and transconductance amplifiers. Okay, and then amplifiers have limited frequency response, and we know the roll-off, the gain of AC coupled amplifiers rolls off at high frequencies. The gain of DC coupled amplifiers rolls off at high frequencies due to unwanted parasitic capacitance. For AC coupled, there's also going to be a low frequency roll off due to coupling capacitance. Okay, so AC coupling, there is roll off at both the extremes. DC coupling, there's only high frequency roll off. Okay, so that's the idea of the big picture of amplifiers. Questions, please.
Professor, like, is there a particular formula if we need to find the Thevenin voltage, like open source voltage?
Yes, the best way to do that is to you can apply the test voltage, test current method to find the equivalent resistance looking into the circuit.
Okay.
Okay.
And the Norton current, do we use the same thing?
Yes, you can translate Thevenin equivalent to Norton and Norton to Thevenin. A current source with a parallel resistance is Norton, and a voltage source with a resistance in series is Thevenin. So the idea is the idea of Thevenin is if you have a black box, okay, and you're connecting this black box to some load, okay, can I represent all of this black box using just voltage, some Thevenin voltage with a resistance in series with this load resistance RL, okay? And I can do the exact same thing. Can I represent this using some current source with a resistance Thevenin, a Norton's equivalent, a current source? So in other words, the idea of finding a Thevenin equivalent comes down to finding one voltage source with a series resistance that is representative of the whole circuit at those two terminals. Okay, these two terminals. That's the idea. Okay. Now let's move on to the other chapter, which is operational amplifiers. Okay, I want to give a minute for the backup to finish. Okay, operational amplifiers, a basic building block, a fundamental building block in many applications. You can build up filters, you can build up summing circuits, you can build up amplifiers, you can build many kinds of integrators, differentiator, many kinds of circuits using OpAmps, a basic building block of many analog circuitry. Okay, it is the idea of operational amplifiers. It becomes all the more wonderful when we use it in conjunction with negative feedback. Okay, negative feedback is a good thing when it comes to electrical circuits. We use this. So typically, op-amps are designed to have extremely high gain. Okay, then what you do is you connect them in negative feedback configuration to trade some of that gain for something else, for some bandwidth. You can trade some of the available gain for something else to gain something else in the circuit. Okay, so what we are going to look at are the characteristics of ideal op-amps. Okay, the characteristics of ideal op-amp, basic amplifiers using op-amps. So how do you build inverting amplifier, non-inverting amplifier, unity gain buffers, summing amplifiers, different kinds of amplified circuits using op-amps. Then we go on to look at the different amplifiers and instrumentation amplifiers, then integrators, differentiators, so on and so forth. Then we look at some of the non-ideal effects. Okay, we first of all begin with ideal effects of op-amps. Then we see how an op-amp can differ from these ideal assumptions, okay, of infinite gain and so on and so forth. Then we summarize. So it's a very interesting chapter using operational amplifiers. Okay, as you can see, op-amps are a key building block in feedback systems. Okay, you use them in discrete 741 op-amp, and you also use them in integrated circuits a lot. Okay, they are often used in conjunction with negative feedback. Negative feedback makes everything better. Okay, and I'll show you what exactly I mean by negative feedback. You get a more accurate gain. Okay, a gain that is independent of P, V, T, process voltage and temperature variations. Okay, a gain that is more accurate and constant, higher and lower output resistance. Okay, if you want a high output resistance, well, negative feedback will give you that. If you want a lower output resistance, well, negative feedback will give you that too. So negative feedback will give you whatever works best for your configuration. Okay, if your amplifier needs a low input resistance, well, you got it from a negative feedback. Okay, if you want a large output resistance, sure enough, negative feedback will give you. And in addition to that, you can get higher amplifier gain in a closed loop configuration, higher bandwidth. Okay, we have to pay for that. There's no free lunch. So for all of the wonderful advantages of negative feedback come from the fact that it trades with the open loop gain. Okay, so the idea is you begin with an op-amp that has a very, very large gain. Okay, something that has a very big gain, a gain that is not, you don't need so much gain at all. Okay, so what you do is you trade that extra gain to to receive some advantages in terms of bandwidth and other parameters. Okay, so op-amps are designed to have very high open loop gain, 10 to the 5, 100 dB, or 10 to the 6, so on and so forth, with the intention of using them in closed loop feedback configuration. Let me show you what I mean by feedback configuration. Okay, so here is your op-amp. That's your op-amp. So if you design an op-amp with a gain of 100,000, that's from here, Xi to X0. Okay, so if you do X0 over Xi, this is called open loop gain. Which can be very large, 100K in this case. If you design your op-amp to have a very large gain, a gain of 100K, that's what it is. But then pay attention to additional circuitry, what you're doing here. There is more magic that we are doing here. Okay, what I'm doing is I'm taking a part of the output, feeding it back into the input. Okay, feeding a part of the output. Okay, let's say the output is 10. Okay, a part of the output, let's say this beta is 0.1. So what I'm doing is, in effect, a fraction of the output, 1/10 of the output is fed back into the input. Okay, this typically happens. Let's say you want to control a thermostat. In control systems, this often happens. Okay, so this is your thermostat that is, let's say this is your furnace. Okay, that's the furnace that is supplying heat. Okay, it continues to supply the heat. Okay, as long as the thermostat meter here, the thermometer here reads 75 degrees. The thermostat reads 75 degrees. Well, how do we know when to stop? Well, in order to know when to stop, we have to feed the status of the output back into the input in terms of an error signal here. So that's the idea in control systems, in systems where we have to read the output in order to control the input. A feedback configuration is used, okay? So we begin with a really large open loop gain. This guy, the op-amp, is said to have a large open loop gain, okay? We design it so that it has a large open loop gain, 10K. Then what we do is we tie some of the output. This is called negative feedback, because pay attention to this sign here. We are subtracting a fraction of the output from the actual input. Your input is X of S, and you're subtracting a small fraction of the output from your input. That gives your X of I. Okay, there's a rich theory behind all of this. The one thing that we want to understand is there are two gains. Okay, the gain from X of I to X of 0. So this is X of 0 over X of I is called the open loop gain. That is much, much bigger, and you want it to be much, much bigger compared to the closed loop gain. The closed loop gain is not from XS, no, it is from here. It's not from, sorry, it's not from XI. The open loop gain is from XI to X0, right? But the closed loop gain is from XS to X0. Okay, so the overall gain, closed loop gain, is the output X naught over XS. Okay, that's the idea of closed loop gain. Okay, the gain of the feedback amplifier or the closed loop gain is defined as X naught over XS. Okay, now the gain of the feedback path or the feedback factor, remember I was feeding in a small portion, a 0.1, a fraction of 1/10 of the output back into the input. That guy is called the feedback factor. So beta feedback factor is defined as XF over X naught. Okay, remember this guy was 10, this guy was 1. So beta was 1 over 10 in that case, or 0.1. Okay, I mentioned that a part of the output is fed back into the input. It provides us with many, many advantages. Okay, so you will often see that the closed loop gain AF is much smaller than the open loop gain A. Okay, and that's a good thing. Okay, when we do the math, this is what is going to come out without a lot of time, without spending a lot of time on the math. What we want to remember is the closed loop gain AF. Okay, the closed loop gain, that guy AF, is defined as A over 1 plus A beta. Okay, 1 plus A beta. And if A beta is sufficiently large, then I can ignore. See, the assumption I'm making is that under the condition that A beta is really, really large, then 1 plus A beta can be approximated as A beta. Okay, so I can neglect this 1. If A beta is much larger than 1, then the overall loop gain is 1 over the feedback factor. That's a really neat technique. You can implement this feedback factor using a resistance a resistance, a ratio of resistances. Okay, so the idea is your overall loop gain, closed loop gain, is independent. This is really insightful, sweet implication is it does not matter what the value of A is. You see, the overall gain, there is no A term in here, there's only beta term. So magically, somehow, as long as the value of A is large, the overall loop gain is insensitive to the open loop gain. Okay, so typically what happens is the open loop gain depends on the process, voltage, and temperature. It has a lot of variance. So what we have done is we have eliminated the dependence of gain over a lot of variables. We made it a really clean, simple equation, 1 over beta. That's the idea. So overall loop gain, AF, is not a function of the open loop gain as long as A times beta is much greater than 1. And this is possible when A is really large. Okay, so that's the idea. That's the idea of negative feedback. That's the idea of making the overall loop gain independent of the open loop gain. Does that make sense? Okay, this guy. Okay, that amplifier, the circuit there can be implemented using an op-amp. Okay, this is the typical symbol for an op-amp, a triangle with 2 inputs. Okay, you apply the inputs to the negative and the positive terminals. There is 1 output shown here. There can be 2 outputs as well. There can be a differential output as well. Okay, op-amps, in addition to the inputs, they do require a positive and negative power supply. Okay, they do need, when you're connecting your op-amp on a breadboard or anywhere, even in an integrated circuit, they do need power supplies. Just that we don't want to show them explicitly, because as engineers, we know that there is no free lunch, even though they're not shown here. The circuit here does not show power supplies. That doesn't mean they don't need power supplies. It's just that they're not shown here. It's understood that there is some power supplies. Okay, the power supplies are not shown here explicitly. However, we need VCC and negative VEE for this op-amp to amplify a signal. Okay, so op-amp shown with this triangle signal has 2 inputs, and for this class, 1 output. 2 inputs, 1 output. Okay, let's see some characteristics of ideal op-amp, and I'm going to these are assumptions that we will revisit later. Characteristics of ideal op-amp is that op-amp always has both a positive and a negative input to make it easy to apply negative feedback around them. So there's always, so when you want to apply a negative feedback, you tie it back to the negative terminal. Okay, like I mentioned earlier, you remember, go back to the feedback configuration here. The output, okay, the output is subtracted. Okay, there is a negative term over here. The output is subtracted. Pay close attention to the fact that there's a negative term over here. It's subtracted from the excess. Okay, Xi is going to be XS minus XF. Okay, that's the idea. That's the idea of negative feedback, the fact that you're subtracting. So that's exactly what we do when we want to apply a negative feedback. What we do is we tie a part of the output to the negative terminal. Okay, that's the idea of a negative feedback, which is a very useful technique. What happens when we tie it to the positive feedback is a whole different area that gives us oscillators. Okay, positive feedback gives us oscillators. Okay, we'll that's beyond the scope of this class. So let's quickly look at some characteristics of ideal op-amp. So there is always a negative terminal. There's always a positive input terminal. So there is this V1, which is applied to the negative terminal. There is a V2, which is applied to the positive terminal. The output can be single-ended or differential. Okay, so see the relationship between output and the inputs. The V output is always an amplification of the difference between the two inputs. So let's say I apply some voltage V2 over on the positive terminal and V1 on the negative terminal. An ideal op-amp or an op-amp really amplifies the difference, V2 minus V1 is multiplied by a gain factor A, and that is shown as the output. Okay, the output of an op-amp is an amplification of the difference between the input. Okay, that's the important thing that we want to remember here. Okay, output is an amplification of the inputs. Okay, so output is usually for our class measured single-ended with respect to ground. Okay, and then we don't show the differential op-amp here, differential output, which there's no reason why we can't have two outputs like so, differential outputs, O output positive, output negative. Okay, it's still possible, but just beyond the scope of this class. Okay, in this class we only have one output terminal, two input terminals. Okay, so let's look at some characteristics of ideal op-amp. Okay, the assumption is that the gain of an ideal op-amp is infinity. Okay, the gain of an ideal op-amp is infinity. So let us see what it means. V out is always defined as A times V input 2 minus V input 1, okay, which is shown as V2 minus V1. Okay, let's pay close attention to this. Let's say the output is some, let's say the output is a non-infinite value, 10 volts. Okay, let's say the output is 10 volts, and the assumption is that the gain is infinity. Okay, the gain is infinity. So the value V2 minus V1 will invariably go to 0. So because this is assumed to be a non-infinite value, 10 volts, and this is assumed to be infinity, when you do V out over V in, it's going to come out to be 10 over infinity, which will be by necessity 0. So the idea is, the first assumption is that the op-amp open loop gain, the op-amp gain is infinity, which leads to a direct consequence of this assumption is that there is 0 voltage difference between the positive terminal and the negative terminal. Okay, there is a virtual, it's almost like there is a virtual connection between these two terminals, even though it is not shown. Okay, so the idea is there is a virtual short between the two terminals. If I apply a positive voltage, if I apply some voltage over there, that's going to show up over here, owing to the fact that the amplifier has an infinite open loop gain. Okay, that's first assumption, and all of these will become more clear when we look at some problems. Okay, the second assumption is that there is the infinite bandwidth, meaning that the op-amp can handle any signals of any high frequency. Okay, the op-amp can keep up with the extremely high frequency signals as well, which is in reality not the case. Op-amps do have a limit on how high frequency can be properly handled. Okay. The other idea is that input resistance is infinity. Okay. If you're looking into, let me clear this up a little bit. The first assumption is that the open loop gain is infinity. Okay. The first assumption is that the open loop gain of an op-amp is infinity. That's one assumption. AV is infinity, assumption one. The second assumption is about infinite bandwidth. The third assumption is the resistance looking into the op-amp, Rin, is infinity. Rin is infinity simply means that the current going in, I1, is 0 and I2 is 0. So the idea is the current going into an op-amp is 0, is another assumption that we make. Okay, and then the third assumption is that the output resistance of the op-amp or output is 0. Okay, is 0 gain for common mode signals, so on and so forth. So there are certain assumptions that we make. If there is a signal that is common to both of these terminals, terminal 1 and terminal 2, then the op-amp should provide a 0 gain. Okay, it should reject common mode signals. So 4 assumptions, 1, 2, 3, 4, 5 assumptions actually. The first one is that the gain is infinity, the bandwidth is infinity, the input resistance is infinity, the output resistance is 0, and then the gain for common mode signals is infinity. Okay, these are the assumptions, and I'll show you how these assumptions become, how we use these assumptions when we are calculating different configurations. Okay, so the same signal, there are some certain definitions here for differential mode and common mode signals. Okay, there are some definitions that we will follow, and I'll talk about that really quickly. Questions so far, please. Okay, some definitions.
Can you hear me?
Yes.
So there's no output at all if the terminal.
Oh, there is output. I can connect a load here, RL. Okay, just that the fact is R0 is assumed to be 0. Does that make sense? So if we talk about in terms of the example that we discussed earlier, remember there is a commission resistance and then the cash out resistance. There is a commission and then there's a cash out. So the assumption here is, and it's purely an assumption, is that the commission component is 0. There is no loss. All the output here is going to show up as the load. Does that make sense?
Professor, I have a question.
Yes.
So like the current through our input terminals, like why is it 0?
The current through the input terminals, right? typically what happens is when you're doing an op-amp, okay, the way you design an op-amp using MOSFETs is using a differential stage, okay, differential stage using NMOS transistors, okay. We will look at op-amps in the coming classes, okay. The gate is floating for an op-amp. The current going into the op-amp is really zero. It's the voltage between the gate and source that generates a current ID in the MOSFETs. Okay, so the idea is, the assumption is that looking into the MOSFETs, you see gate of a MOSFET over there, and you see another gate of a MOSFET over here, in which the gate is floating and there is no direct current flowing to that. Okay, for now you have to trust me on the idea that the current flowing into the MOSFET, into the op-amp is zero, owing to the assumption that the R input looking into the op-amp is infinity. Does that make sense?
Yeah, like, is there any like concept of like virtual ground, something like that?
Yes, virtual ground is coming from this guy. Okay, infinite gain. Let me talk about that. Okay, let me spend a little more time on the idea of virtual ground. Okay,
Sorry,
let me talk about.
sorry, my question I had before was the last ideal op-amp assumption, the zero gain for common mode inputs. Does that mean
Yes,
that there's no output if you get two inputs are the same, or does that mean you just have zero gain?
yes,
You get that the
yes.
output is the input?
When you tie these two together, okay, I'm sorry I missed your question earlier. Okay,
No worries.
if you tie both of the inputs like so, okay, and you apply a common mode voltage that is common to both the terminals, the output is going to be zero.
Okay, thank you.
Okay, okay, I'm sorry I did not get your question earlier. Okay, so that's the idea. If you only the difference between these two terminals, this terminal, the voltage between these two terminals is amplified. Now let's look at the idea of infinite gain. Okay, so or virtual ground. I'm not going to talk about virtual ground yet. I'll talk about virtual short. Okay, virtual short. So the idea of virtual short is conceptual. There is no short between these two terminals. Okay, all we know is that if I apply V1 to the terminal 1 and apply V2 to the terminal 2, V output is going to be A times V2 minus V1. Does that make sense? Are you with me?
Yes.
Okay, now let's see. The assumption is that V out is not infinite, right? It is finite. Correct?
Okay.
And this guy, the assumption is that this is infinite. Yes?
Yes.
So what is V2 minus V1? V2 minus V1 is V out over
Divided with.
A, right? So something finite divided by infinite should give you a value of 0, right?
Mhm.
So the
Yes.
idea is the voltage, there is no voltage difference between this terminal and this terminal, correct?
Okay.
So it's as if conceptually very similar to shorting them together, okay?
Okay.
So if I were to tie this to a ground physically, then this will also be virtually tied to ground, and that's the idea of a virtual ground. Does that make sense?
Yes.
So all of the concept of virtual ground stems from the assumption that the gain is infinity or very close to being a very, very large number, very close to, for practical purposes, it's infinity. Make sense?
Yes.
Okay, so these are the assumptions. So we'll come back to using these assumptions again and again, again and again. The idea of infinite gain, the idea of zero current flowing into the op-amp, okay? And then there is no output resistance, okay? We'll come back to those assumptions again and again. So the loop gain, not the loop gain, the open loop gain is infinity. The input resistance is infinity. We'll come back to work on those. Okay, so let's see. Here is an op-amp. Okay, let's say this is an op-amp. What I'm going to do is, let me first so I have an op-amp that looks like so. Now I'm going to rearrange some of these voltages, redefine them, and look at them from a different perspective. Nothing is changing except the perspective. Okay, I'm going to define the two inputs in terms of two new variables. Okay, they're still the same. The operation of the op-amp is still the same. Okay, except that I'm going to express V1 as a new voltage, V2 as a new voltage. So in terms of the operation, in terms of the values, nothing is changing. Okay, so I'm going to define a new term, VDM, V differential mode, which is defined as the difference of the two voltages. Okay, let's say this is 7 volts, let's say this is 3 volts. The difference between these two, okay, that's 4. Okay, it's easy to see if you see that number, if you plug them in as numbers. Okay, so I common mode is defined as the average. So average, and this is the difference. The average of those two inputs is defined as the common mode. The difference is defined as the differential mode. Okay, so let's stick those with those numbers. Let's say this is number 7 and this is 3. What is the VI differential mode? 4. What is VI common mode? 5. The average is 5. The difference is 4. Okay, so now the neat thing is one of the voltages can be expressed as V input common mode plus average over 2, while the other number can be expressed as V1 can be expressed as V input common mode minus V average over 2. Okay, so a number above average, a number below average. Okay, if average is 5, 5 plus 2, 5 minus 2, 5 plus 2 is 3, which is sure enough same as that. 5 plus 2 is 7, which is same as this. So the idea is the midpoint between those two values is average. Average plus, so this is average, let's say, I'm sorry. So average, one of the inputs is average minus difference by 2. This guy is average plus difference by 2. So you take any two numbers, 10 and 20, You average them 15. The average plus difference by 2. Difference by 2 is 5, 2.5. And the other is average minus 15 minus 5. Okay, so this guy is the average. And this guy is difference by 2. Okay, difference by 2. Okay, simple arithmetic definitions. Okay, so that's the idea. So one number gives you 20, the other gives you 10. So the idea is pretty straightforward here. So I'm going to define two terms. One term is the difference. One term is the average. Okay, average is one term and the difference is one term. Okay, one voltage is average minus difference over 2. The other voltage is average plus difference over 2. So it's a rearrangement of these numbers and nothing else. So it's useful to think of the inputs and outputs in terms of the differential mode and common mode. Okay, and we'll come back to talking about that later. Questions so far, please? Okay, so this is only all of this definition of differential mode and common mode signals is to see what is the average signal and what is the negative peak and the positive peak. Okay, so what we will do is we'll stop here, come back in the next class and continue this. Now, what time is our class again, the lab?
No.
At noon, right? Okay, so I'll see you folks back at noon. We haven't, how many of you received the lab kits yet? How many of you received the lab kits already, by a show of hands? Okay, pretty good. Good, so you're all ready to start working. Even if you did not receive your lab kits, the first lab does not have you implement any hardware. So it's only software. I'm briefly, quickly going to go over that lab in the beginning around noon at 12 o'clock, and then let you work on that. Okay? We'll see you folks.
I'm sorry, is the pre-lab just the hand calculations or?
For this lab, the pre-lab and the main lab, there are no two components. So just the hand calculations. And if you're done with the simulation as well, that's fine too. But by the end of the day today, if you can show me the hand calculations and the simulations, then you're good to go. From the next lab, where there is hardware and simulation, I want you to work on the calculations and simulation for the pre-lab. Okay, now pre-lab is just the hand calculations.
Okay, if we don't finish by the end of the lab period, can we email you the results or?
You can email me the results, but it'll be a nightmare for me to take a demo of it. Okay, so I would say spend as much time as you can in the lab to finish up the lab work before the end of the day.
Okay.
Okay. All right, I'll see you folks back at noon then.